Hi and welcome to this live video demonstration of cutting force analysis using MachineWorks. My name is Richard Baxter. I'm Head of Sales and Marketing at MachineWorks Limited, which is a company that makes both the MachineWorks CNC simulation libraries and the polygonal libraries for polygon mesh processing. So first of all, MachineWorks has been able to assist with very good quality cutting force analysis for many years now. But we have made some new changes in the latest release and some new example code. So part of this update is just to tell you a little bit more about those. So typically when you are analyzing the cutting force on a tool as it's cutting stock, you want to know things like the volume of material removed, the engagement, the depth of the engagement on the left and right side of the tool, etc. And MachineWorks, because it's a polygonal solid model, it can give you a full intersection solid of each cut as it happens. But our customers generally take that and then they analyze it, and in a lot of cases they're mostly interested in the leading surface of the tool, so what the tool is doing at the end of the cut and how it engaged with the stock at the end. So there's now a new API called engagement surface that basically computes that for you. So if you look at these images in the top right here, the image on the left is the full intersection solid, so that's the intersection of the intolerance swept volume with the intolerance polygonal solid model, whereas the image on the right is just the engagement surface, so it's just the front faces of that intersection solid. The other thing we're going to show you is a new WPF example. So it's written in C#. It uses the supported MachineWorks C# wrappers. So there's no C++ CLI or anything like that going on here. And it uses OpenGL, so it shows how you can get OpenGL to peacefully coexist with WPF, which is not always straightforward. And it's available as unsupported example code. So if any of our customers are interested, then just get in touch and we can send that to you. So what are we going to demonstrate here? Well, this user interface I'm going to talk through more in the actual demo. But basically, it shows you the standard values that MachineWorks MachineWorks has had for a while. They report the volume of material removed and the left and right width of the cut, from which it's easy to compute the engagement angle. It's also going to show you the engagement surface versus the intersection solid, which I've already talked about. It shows you how we can, how MachineWorks can slice those. So slicing is useful in this context, really just as a way of making the calculation simpler. But you can create many slices through these surfaces or solids and use those to do your own calculations. And finally, we've created a nice little plot here of the depth of cut versus the width of cut using polar coordinates, which has come from the slices created here in the image on the right. I also want to point out the advantages of using a polygonal model as opposed to a sampled model. So in a polygonal model, what we mean is a polygon mesh where there is a topology such that you can walk from one face or triangle or n-sided polygon via an edge to the next one. So it's a closed continuous surface, and that's the model that has been the sort of main model used by the MachineWorks Visicut engine since MachineWorks was started 30 years ago. So most of our customers these days use the Visicut engine for most of the simulations. But Visicut also has a sampled engine, and by sampled, I mean other phrases for sampled are things like voxels, dexels, tridexels, or whatever. The Visicut sampled engine is, we used to call it sample cut, but it's now just hidden behind the Visicut API, so it kind of doesn't have a name. It's just the sampled mode of Visicut, and it's based on tridexels. So it's a fixed grid of points in space. Which has its advantages. It's a lot easier to compute. For a given grid resolution, then you have a fixed size in memory, etc., etc. So it's got definite advantages, but it has some specific disadvantages, particularly if you need the accuracy for doing physics-based calculations of things like cutting force and forces on the tool, etc., etc. And these, I know they're hard to see, but these two images show you an example of that. So this is quite a reasonable close-up of a stock that's been cut with a ball end cutter. Sorry, not a ball end, a bull nose cutter with a reasonably small radius, such that the radius of the bull nose tool is similar to the distance between the sample points. And you can see we get a very, very nice result in the polygonal model, but the sample model has a lot of noise. And this is where, when you have this sampled grid, you've got a grid of points, and you don't know what the data is between the points. So to create a polygonal model for rendering or whatnot, you have to actually interpolate between those points and try to project edges and do intersections where, or project faces and do intersections where edges might be, etc. And that kind of works well most of the time, but it does break down in certain circumstances, and this is just a nice example of where it breaks down. So all these jaggies here are basically where, in effect, because of the curvature of the small radius on the tool, things are just basically broken down. Now, I mean, this is not unique in any way to MachineWorks. If you zoom in, or to your zoom into any kind of verification engine in a system that doesn't use MachineWorks, and there's a fairly good chance you'll see similar things like this. And it's not I've not taken this as a contrived model. It's a real model that somebody gave us. So it's by no means designed to make the sampled code look bad. It's just what you get if you use sample technologies. And people have put a lot of effort into mitigating it and avoiding it and hiding it, but the bottom line is it's a feature of that kind of technology. That can be, I mean, generally, if you're just doing visual verification and you want to catch clashes and things like that, and your tolerances are relatively loose, then it's not a big problem. I mean, it's a good system, it works well. But if you want very, very accurate results, specifically for physics-based analysis, and you're working with things like thin tools or tools with small radii, like I've just described, or you have like very, very thin, almost scraping cuts, you might have very highly accurate cuts. Or the other problem is if you have very, very large area stocks, so you haven't got enough physical RAM to decrease the distance between your grid points, then the sample technology can become a problem. That's why we're highlighting, or this demonstration is designed to highlight, or partly highlight, how you can get very, very nice results in this area using the polygonal technology. Okay, so that's enough preamble. Let's go on to the actual demonstration. So on with the demo. I've loaded in a simple LWN file called simple.lwn. So LWN is MachineWorks generic CL-like cut data format, basically. So it's just do cut to coordinates, etc. And there's 3 stocks defined, and we're going to cut those with different tools. First, I'll turn on cutting info and also live updates. So cutting info says calculate the cutting info per cut. Obviously, there's an overhead to doing that, so we turn it off by default. And then live updates says let's actually update the graphical user interface. So let's update the graphics and all the cut information every time we do a cut, basically. And then this table here shows the cutting information, volume and material removed, the maximum depth, and the left contact and right contact, the maximum width, minimum maximum width on the left and right. And then I'll just do a cut so you've got something to look at. So top left view is just a standard simulation view, what you'd normally look at in a graphical simulation. The top right view is the intersection view, which is the intersection of the tool, of the swept volume the tool makes during the cut with the solid. Now, let me just turn that off, and so that is the actual swept volume. So that's the solid boundary surface of the volume of material removed by the sweep during the cut. But in MachineWorks 8.6, what most people seem to want is actually the engagement surface, which is the faces of the stock that are touching the tool at the end of the cut. So we've also added something to calculate that, and that's what you can see here. But for the rest of this introductory demo, I'm just going to keep the swept volume on because it's clearer and easier to see what's happening. Down here we have the slices, so we call them intersection profiles. So they are 2D slices through the volume that's of the material removed. Let me just turn camera tracking off, turn it to that view, turn that, and then we can rotate that. So if I rotate that, whoops, let's get it a sensible direction. There we go. So here we can see we've sliced that swept volume. Now we've sliced it with a lot of slices and we're only showing some of those, and we've got more slices at the bottom and the top because that's where, when we were testing this, we saw that we spotted visual anomalies, like why is that like that? And quite often the reason was, well, actually we haven't done enough slices there. So that's one thing that's important to note. But you can actually control how many slices you get and the distance between slices. You can pass an array of heights, etc., etc. And then those slices are used to create this graph on the bottom left, which is a graph of the height or the depth of material at the end of the cut, in effect on the engagement surface, plotted in polar coordinates, so from minus 90 degrees to 90 degrees. So as you can see here, it's a constant height, as you'd expect, and it goes all the way from minus 90 to 90. And that's computed from these slices. This isn't part of MachineWorks, the graph, it's just something we've added in this demo for illustration purposes, but the source code is available if you want to take a look at it. Okay, so I'm going to put that one, first of all, back to the top view and put camera tracking on. So as the tool moves, this view will stay centered on the tool, just so you can see what the slices look like from the top down. Okay, so let's just do some more cuts. So that's a cut with a ball nose tool. There we go. So you can see it looks pretty much how you'd expect. And here with a ball nose tool, so flat bottom and radial fillets on the ends, and you can see, yeah, that looks pretty much how you'd expect also. And then we'll do some cuts on the side. So this one is on the right. If I switch back to cutting info, we can see now that there's no contact on the left. There is contact on the right, and the maximum contact is 10, which is the radius of the tool. So that's all good. And you can see that the graph looks right and the intersection profiles look right. And we'll do a few of those, ball end and ball nose, and do them on the other side. Yeah, so there we go. Now we're going to do a very, very thin scraping cut. So in this case, we've moved the tool. So the tool radius is 10. We've moved the tool 0.01 to the right to do a cut with a thickness of 0.01. And you can see here, we've got a very, very thin solid material removed. So if I turn that off, and actually let's just look at that solid and zoom in, you can see, yeah, that is pretty thin. You know, keep zooming, and eventually we get to the, oh, yeah, hard to rotate. If I put my camera, then we can rotate. So we get, you know, there's the edge of it. So it's thin, but we can go a lot thinner. There's, you know, it's 0.01 isn't that extreme. Let me turn those things on. The other interesting thing here is if we look at this cut data on the right, the contact to the right is 0 to 10, that's what I expect. And if you look at the graph, it looks kind of like what we'd expect. But if you look carefully, you can see it's just shifting over to the left of the 0. Okay, why is that? Well, we've had to move the tool in by 0.01 to get this cut. So if I actually turn these off again and zoom right in on this, I'll keep zooming. There we go. Oops, sorry. There we go. We can see it's correctly picked that up, and that's been highlighted by the slicing and the graphs. So we've got good quality data here. I mean, as with anything, there's a trade-off between accuracy and performance. But the nice thing about the MachineWorks polygonal model is you can set the tolerance you're working with on a per tool basis, and you know that MachineWorks sweat volumes are going to stay within that tolerance. So you know the results you're going to get are within tolerance. With a sample data model, you don't know that. I mean, the point where you have sample points, you might have extremely accurate data, but in between those points, you know nothing. And that's a pretty important issue when you're dealing with these kinds of problems. Right, let's turn everything back on. So I'm just going to step through the end of these. So there's the ball end version of that, there's the ball nose version of that, and let's do it on the other side as well. Okay, so that's the end of the first example. Okay, so let's move on to a simple 5-axis example. So the same 3 cubes and similar cuts, but this time 5-axis cuts. The observant among you will notice that the date and time at the bottom right has jumped forward a couple of weeks, and also you might feel my voice sounds a bit different, which is because I've got COVID. So the reason for re-recording this segment is that when it was reviewed by the development manager, he spotted a small bug in the engagement surface, which is now fixed. So we thought it was worth actually redoing this segment of the video, and also it kind of shows how useful these kind of simple examples are in analyzing this stuff. So first of all, I'll just do a simple cut with a flat end tool, and it's a 5-axis cut. And if we have a look at that cut there, the engagement surface, you can see that part of the engagement surface is behind the center of the tool. And so the engagement surface is the forward faces at the end of the cut that are engaged with the stock. And so because the tool is tilted, that includes faces on that are behind the leading edge of the tool, if you like. So that is correct with the current definition of engagement surface. If we look at a ball nose cut, so it's the same cut, and this time I'm going to look at the intersection solid just to show you what that looks like. So there's the intersection solid. As you can see, it's a nice 5-axis. It's been created by doing an intersection with a nice 5-axis sweep with the cuboid stock. But I'm just going to turn that off mainly because it's easy to see what's going on. If you just look at the engagement surfaces, these cuts can get reasonably complicated if you turn everything on. And there's the slices. Again, as I said before, we're only rendering some of the slices that we use to create the graph, not all of them, just to make things clearer visually. Let's look at that at the top. And let's continue with bull nose and then some side cuts. Same thing. Other side. And then I'm going to look at a thin cut. So actually, let's look at the ball end tool. So we've got a very thin cut here. So let's actually look at the intersection solid, and you can see we've got a thin intersection solid. It's the same as it was in the previous example, 0.01 thickness, but what you can see is there's a very clean result here. This isn't something that's been reconstructed from a Dexel or a voxel grid. It's an explicit polygon mesh. It's a explicit Boolean operation of 2 meshes, the sweat volume and the in-process stock. So there's no kind of reconstruction from sample data going on or anything like that. Let me turn that off again, and let's just finish this off. So just show you the cuts at the ends. So thin cuts on both sides. Okay, so that's the end of the simple example. We'll now move on to a couple of more challenging examples. Okay, so let's look at a more substantial toolpath. We're going to look at this 5-axis finishing cuts of a propeller. Whoops, so there we go. So the first thing to point out is this isn't a real toolpath from a CAM system. it's something we've knocked up using Polygonica, which is our other software library for general mesh operations, but also operations on polylines and polycurves and curves lying on a surface and stuff like that. So we've been able to use that to sort of create a sort of reasonably convincing toolpath if you don't look too closely. And this is actually the result of the roughing cuts of that toolpath. But we'll have a look at the finishing cuts. So there's going to be two sets of tools used here. So let me just zoom in, and everything's turned on, so let's set that going. Okay, so you can see, there we go, we can see the engagement surface being calculated there. Which one? It's a bit hard. Oh, the tool's coming around this way. Yep, so it's a bit hard to see, so I'll maybe turn it like that. It's a bit better. And yeah, we're slicing that as we're going along, and we're updating the graph as we're going along. I'll turn on the full intersection solid, so we're displaying that this time. And because the cuts are quite short, there's not a huge difference between the intersection solid and the engagement surface, but you can just get a general idea. If I look at that and zoom in, you can see there's the actual solid of the intersection. Okay, so next thing I'm going to do, let me turn that off again and set some sliver detection on. So I'm going to set that to 0.1 and a height of 1. So let me just set that running. Sliver detection is just something we've added to this demo that just says basically if the thickness of the cut, okay, I'm going to update the graphics once every 10 cuts as well. If the thickness of the cut is about less than 1/10 of the radius of the tool, then stop, in effect call it a stopping condition, so that we can find a reasonably thin cut. So there aren't any in these finishing cuts because it's removing, or in these first set of cuts because it's removing quite a lot of material, but okay, here we go, it's found one here with these deliberately thin cuts. So you can see, let me turn that one off and show the sweat volume. So you can see we've got a fairly thin cut there. If I hide it, and let's look at the other side, you can see the tail end of it is very thin indeed. So again, and if you're trying to pick these things up and analyze them using a sampled technology, you've got a fixed grid of points that are fixed distance apart, and you can increase the density of the points, but you're increasing your memory on effectively it's a volume, so you're increasing the points in each direction or in each axis, so you're increasing your memory rapidly, and you're still risking missing. One cut could happen to graze one set of sample points, the next cut might slightly miss them, and then you're going to get a very big difference in the things like the volume of material removed from one cut to the next, even though the cuts are doing almost the same thing. So that's why people find the intolerance polygonal technology of MachineWorks more suitable for this kind of analysis, because the only tolerance you're controlling is the tolerance on the tool, and the sweat volume that's being created is guaranteed to be within that tolerance, and that tolerance is then transferred to the stock model during the Boolean subtraction. So you get you get an answer that is within the tolerance you've specified. It's not dependent on the resolution of the grid points. Okay, I think there's one more of these. Let me just see what happens if I run it like this. Oh yeah, there's the next one. So it's jumped forward a few cuts, and there's another one of these that it's stopped at the sliver, and it's a similar sort of thing. So there you go. Okay, let's turn everything back on. I'm going to turn sliver detection off, and we'll just run a few more cuts just to see. Let's look from that side maybe. And just run a few more cuts, and you can see it finishing off this toolpath. Okay, I think that's probably enough. Okay, and as a final example, we'll show another 5-axis part. Those of you who've been using MachineWorks a long time will perhaps recognize this impeller toolpath, which I think we got in the 1990s from someone who was testing MachineWorks. So it's, let's say everything's turned on. Let's just do some cuts. It's yeah, so it's quite an old toolpath, but it's still kind of quite nice because the tool is cutting along the side of the stock, so it's doing a lot of work, and you can see everything's looking pretty good there. If I just stop it and let's zoom in and have a look at the engagement surface, you can see the engagement surface looking pretty good there, which is what we want to see. And I'll turn on the actual intersection solid. Now I'm going to run it with the intersection solid on, so you're going to see some fairly wacky images because the cuts in this are quite long. I think in most CAM systems they would, or on the controller or whatever, they'd be subdivided into much smaller cuts. But in this demo, it's creating quite long swept volumes, and so the intersection solids are quite big, and hence obviously the tool axis is varying a lot during each cut, so you're getting some quite freaky slicing going on at the bottom there, and some nice interesting engagement surface plots in the bottom left there. So let's just look at that one at the end there, and there we can see there's our intersection solid, and there's the slices for it, and there's the depth of cut at the end, so you can see the tool is just coming out of the stock, and the plot of the engagement surface shows that it's at this point it's a very shallow depth of cut. Okay, so that's the end of this demo. If you've got any questions, or you're a customer and you're interested in looking at the example code, or you would like to explore MachineWorks further, then please don't hesitate to get in touch. You can contact us via the website. You can find us on LinkedIn. You can find me on LinkedIn. And if you're a customer, then just get in touch with the support team. They will happily sort you out, or feel free to email me directly. Otherwise, thanks very much for your time. I appreciate these videos are quite long, so thanks for listening, and I hope you have a great day.